My name is Chris Bergh, and we're going to talk over the next sort of 30 minutes about some concept called data ops and how that applies to AI and data science. So the first kind of the theme of this whole session is summarized in this one sentence, and that sort of what you do is much less important than how you do it. And so what does that mean? Well, if you look at, let's talk to some analogies to that. So if you look at manufacturing, and here's a quote from Elon Musk, there's the machine that's built in the factory, but actually the machine that makes the machine has much more importance. If you look at Satya Nadella, who's done a great job turning around Microsoft, if a developer has to choose between working on a feature, and that means like some code that goes into a program, or productivity, the developer should work on productivity. And if you have ever read Deming, who's the father of statistical process control and the Toyota method, that when there's problems, it's almost always the process, not the person. And so if we translate that into data and analytics, there's a lot of talks that you're going to hear in this conference about the model or the algorithm or the data feature or the data pipeline, about data visualization or governance, and even the data itself. And so I think what this talk is about is that how you do it, the process of development or training or deployment or monitoring or iterating or collaborating or measuring results, that actually has much more importance in success of any data and analytics. And I'm going to use the term data and analytics pretty broadly here, data science, data engineering, data visualization project. And so we've been calling this term for the past 6 years data ops. And one of the reasons why this situation has occurred is that data and analytics has a bit of a dirty secret, in that we see that data and analytics is sort of pretty hot and an exciting field, and all of you are attending this conference to learn more about AI and data science and data lakes, and that's fantastic. But it turns out that most of the projects that actually work in data science and data lakes are not succeeding. Most models never get into production. Most organizations who consider themselves data-driven are dropping. Most analytic projects fail, and most things that actually go into production never quite make it. And so what we've been doing is thinking about that and thinking of it as very similar to the way the auto industry in the 1970s suffered under Japanese imports, and that it's slow to change new features. We have a lot of errors, and it's slow to move models or in fact any analytics into production. Likewise, the amount of time that your team spends is actually on things that aren't really related to doing cool new stuff for the customer, because there's a lot of complications in organization structure and roles and tool chains and data and collaboration. And so in a lot of ways, the sort of single person heroic age of data and analytics is over, and we're trying to make the organization productive. And if you think about it, the actual model itself is really a small part of the system that has to do with the training of the model and the deployment of the model and measuring the model and monitoring the model. And if you look at it from a process standpoint, when you're doing data science, you start with a business need, and you prepare data and develop features and build the model and evaluate it and deploy it and then finally monitor it. But this fundamentally is an iterative or an experimental process. And so as a result, I think data science teams, people who do data engineering or data visualization, are suffering because we're all caught between these sort of these forces. One is that there's data providers who give us data that feed into the model are suffering, give you crappy data. Our customers who demand insight really think of us as Amazon, that we should have new insight every day. And then the teams who support us, either it's production or other teams we collaborate with, are very critical. And so what I've noticed is there are a lot of data and analytic teams are sort of beaten down or distraught or disempowered. They can't create and innovate. And we have a lot of cultures that are either rife with sort of heroism that actually ends up leading to retention challenges. So we've been talking about this term of data ops, and it really is a set of technical practices and cultural norms that can help end that suffering. And it's done by focusing not on the model and not on the transformation, but it's really focused on trying to set up a way to enable rapid iteration. It's really about focusing on error rates. How accurate is your model? How inaccurate is your model? How accurate is the data that's going into it? And then collaboration across teams and products, and measurement of results. So these four things: cycle time, error rates, collaboration, and measurement. Again, they have nothing to do with the stuff that you do, but they have a lot to do with sort of the factory, the system, the process that produces it. And so by focusing on that other part, that people and process and technical environment, we think that you can achieve a lot of better results. And for this solution, there's been different terms put out there, sort of model ops and ML ops and data ops. And for this presentation, I'm just going to use data ops to be the superset of them, because I think they conceptually are the same thing. And there's been a lot of discussion on data ops and by proxy model ops. And if you look at it, more and more people are talking about it. There's now probably 8 or 10 talks at ODSC about ML ops and model ops, and I've been presenting at ODSC for my 4th or 5th year, and we were the only ones 5 years ago, so it's nice to see more of the industry catching on to it. And so what I'm going to talk about now in the next 25 minutes is like, what is data ops and what are the 7 steps? And so we've written a book that you can download for free. We've written a manifesto with 18 steps. But if 18 is too much for you, we've got 7 steps plus 3, so that's 10 that we're going to talk about. And we're going to go through each one of these steps and talk about what it means to do data ops. And the first one is orchestrating 3 pipelines. The second one is the importance of tests and monitoring and improving that things work. And then we're going to talk a little bit about version control and branching and the importance of your development environment, and then parameterizing and reuse. And then we're going to go into a little bit of architecture and metrics and collaboration. So the first thing is, at a high level, think of what you do when you have something in production as a factory. And look, if you look at this diagram, data comes in on one side, it goes through a process, and that could be batch or real time, it could be structured data, unstructured data, big data, small data. They all sort of follow the same pattern. And you go through a series of tools and transformations. Maybe you've got a database, maybe you've got a data pipeline tool, maybe you've got a data science platform where you do your models, maybe you've got data visualization tools, maybe you've got a catalog tools. And honestly, there's probably, in each one of these categories, there's probably 50 tools. And you may have your favorite tool. I have my favorite tool. And there's good reasons why you like them. But all those tools themselves, think of them as sort of manufacturing stations where you're creating, transforming, adding artifacts to it. And so this process has to be thought of as a manufacturing line. And that is an important metaphor. The second metaphor that I think is important is to think of what you do from creation, from the ideas that get in your fingertips to getting it out as production as another pipeline, as a pipeline that we call the innovation pipeline, to be able to take your ideas and get them into the hands of your customer. And so, you may use R, you may use Python, you may like to use SAS, you may, like to use a visual UI or code directly, but there's lots of different tools that you use to be able to create. But the idea is, how fast can you create and get something into production? And so the problem is, you need to sort of run this great Toyota high quality assembly line, but you need to be able to take a piece of it, pick it up and iterate and improve. And so you just don't want to learn about errors from your customers. That just sucks. And when they find out that there's something wrong, they complain and you go through a big hassle to fix it. You also don't want to break stuff when you deploy it, because all those things actually end up causing fear and causing problems. And so there's a third pipeline that you have to do, because in order to get things into production, you also have to be able to create an environment to do it, or abstract out the environment. And so there's kind of 3 pipelines here. There's a pipeline that orchestrates what happens in production. There's a set of pipelines that deploy to production, and there's a set of pipelines that help sort of build or tear up or manage your environments that do all those things. And so there's, and if you're interested in this concept, where DataKitchen is actually doing a webinar series about each one of these 3 that's coming up starting next week. So, so given that there's a concept of there's 3 pipelines that you need to do, and in focusing on the world of data ops. You also need to be able to tell if things are working. And so there's two ways of thinking of proving that things work. The first is monitoring or observing what happens in production. And that as your data flows through the system, is it right? Are you going to get one of your customers call you up for an embarrassing error? And then the other one has sort of a different idea. Is what you've done going to break something that already exists? And that is more in the innovation pipeline. So if we look at what happens in production and monitoring what happens in production, again, if in this factory where data comes in on one side and code and algorithms and tools are being applied to it to get a result, you want to know if there's something happening wrong in your assembly line as soon as possible. Did your data provider screw you over? Is your business logic still correct? Did your model go out of compliance? Is it still getting the right set of prediction accuracy? Is it time for you to retrain it? Are your outputs consistent with what your customers have seen before? And the way that we do that is to think about it as a set of tests or monitors. And one of the most important parts is to think of them as different types of monitors. The first is kind of an andon cord, stop the production line. The second is, hey, this is weird. Maybe you should take a look at it, a warning. And think of this system and monitoring it and as a set of data that you can analyze because your production data is worthy of doing data and analytics. And so there's just lots of type of tests, and we don't have time to talk about all the different tests that we have going on here. And so, you know, there's tests that can look at the input, there's tests that can look at the processing, there's different ways to take tests. But one example of a test I would like to talk about is what we call a location balance test. And that in these systems in production, a lot of times, whether it's invariant of data size or shape or system, you know, the data bounces along. It comes in from a source, it gets landed in a bucket, it gets transformed in a database, it ends up in a different zone in a database, it's cached in a model or a visualization layer. And you just want to make sure that if you've got 1 million rows in the beginning, that you're given the equivalent of 1 million rows when you come out the other side. So follow the bouncing ball. Another type of test that I think is really important is to be able to judge whether your customers are correct. And I've had the misfortune of working with data engineers and data scientists and data visualization people and working hard for a month and then presenting something to a customer. And then within 3 seconds, they find out that it's wrong. And one way to do that is to look at something called a historical balance test, which is basically say, hey, these are the important things you saw last week as a business customer. This is what you're seeing this week, and here's the difference between the two, and looking for outliers. And again, it's a simple thing, but you want to be able to make sure that you can prove to yourself that the data is right, that your algorithms are working, that your visualizations are working before your customers do, and try to get away from hope. Because in a lot of ways, hope is your enemy. We as an industry have these hope-based systems. You put something into production, and maybe with no testing, or maybe a couple of unit tests, and you kind of hope that your systems are still working, that your data providers haven't screwed you, that there's not one of your other developers have given you crappy code. And I think the way to solve that is to, on top of all your tools, automatically in production, monitor what's happening, and send alerts and notifications if something happens, and make it easy to create tests. And, you know, I think the real benefit here is that having less errors means that you have more time for innovation and more customer data trust and less stress and embarrassment. And this idea of focusing on errors, and that errors are kind of the superset of data quality or process errors, and kind of loving your errors and embracing that you're going to have an error-filled system and that nothing's perfect, and that the only thing that's bad is to get rid of your hope, I think is really a very counterintuitive notion. But that actually ends up, what we see with our customers, it ends up having these kind of benefits. So the second part of this is trying to look at, well, when I'm in development. And so a lot of good software engineering teams have a metric saying, if I get someone out of college who comes in, how fast can they deploy code in the production? And how much do they have, how many people that they have to talk to? And so can you have a system where you can have that person 2 weeks out of college make a bug fix and deploy to production without having to go through a bunch of meetings? And so that idea is being able to think about what you do in a different way. And so there's a set of tests and ideas that you do in development. Some are called unit tests or functional tests or regression tests or performance tests, smoke tests, end-to-end tests. There's a whole set of types of tests that actually prove that your system works in a development environment before it gets to production. And so what's interesting here, if you look at, there's a sort of dual nature to the test that you have. The first idea is that in production, your code is fixed, but your data is variable. But in development, your code is variable, but your data is fixed. And so if you can imagine that these tests or monitors are shared between the both. In fact, a lot of the tests intersect, and they can be used both in the innovation pipeline and in the value pipeline. And that's why we guide that spending 20% of your time building these automated tests, making sure that they cover the scope of end-to-end, they cover all the cases you want, is really a valuable thing to do. And this isn't these sort of tests and monitors. It doesn't matter what type of work you do. Data, they can be developed in your feature training pipelines or in your production model pipelines. And so this duality of tests, I think, is really important. So kind of going on to the next idea here in our system. So the first idea is that all your work should be put in a version control system. And so what that means is that whether the work that you do in Python or in R or in SQL code or ETL code, your data visualization, all should be stored in Git. And Git is a very good place to keep track of all of it. And it shouldn't be on your file system. It shouldn't be kept in a database. It should be kept in a versioning system. And why is that? Because what you can do, and having Git allows more than one person to work on the same thing at the same time. And that's called branching and merging. And so in this way, you can have, and software developers have been doing this for years, you can have people work on the same piece of code, but be able to merge their results back again. And that enables efficient working. And so the other part of being able to do good work is to also have people work on multiple environments. And in that way, when you do development, you need a place to do developments. And your branching should actually fit into that environment. And actually, these environments that we do, our development, are kind of complicated, right? Because you need test data, you may need hardware and software, you need to have the right versions of software, you want to have the right version of your code, you may want to have some test history. There's a lot of complexity in building these sandboxes. And if we think about that, and I'm kind of speeding through these here in order to make our schedule. Another aspect of what we have to do is be able to reuse or parameterize what we do. So if you think of all the work that happens in data and analytics, a lot of times people are sharing their work by copying and pasting. Mail me that Python file that you did. And then I take it and I copy it and I start using it, and I got my own version of that Python file. And then it spreads out, and the logic in there is copied and paste. And this copy paste engineering actually ends up being problematic. And so try to reuse your code and create functionally reusable pieces. And think of this idea in software being able to refactor or improve your code over time. And then lastly, the 7 steps. If you think of all that work that you do as an end-to-end piece, all the way from getting data to delivering value, well, you should be able to parameterize that. Think of all the pipelines as you do as sort of one big function. And I want to run it with big data or small data. I want to run the front end of it or the back end of it. I want to run it based on last week's data or this week's data. And so parameterizing your process and also taking care of security credentials is very important. So let's look at these 7 steps in action. So a lot of people have different ways of doing their data and analytics. Some people do Kanban, some people do sprint, some people pulse the SAFe method, the scaled agile method, the Spotify method. There's lots of ways to run a team, but they all start off with something called a story or some task that you have to do. And so if you select a story and then you create a branch, which is in Git, you create an environment that runs in the branch, and then you implement the work that you do. And maybe it's a feature development for a model, maybe it's a visualization. You can train the model in here, you can write new tests, and then you can run new and existing tests to make sure that update to the model with a new data feature actually works. You can check that code into the branch, merge to the DataKitchen, and then delete your test environment. And then when the sprint ends, you deliver all the completed features to the customer, merge the sprint branch to the master, and then perhaps roll unmerged features into the next sprint. And so this process of following these 7 steps is the way that we think that it's a better way to work. And if you look at it from a data science standpoint, these 7 steps actually fit right into the process of feature development, model building, and model deployment. So if I go on to my other 3 steps and think about how this works. So the first one is data architecture. And so we talked about in this, if you came in thinking about data architecture, here's the discussion. So first of all, I've been in the field many years, and every company's got a data architecture, and they've all sort of have the same diagram: data on the left, customers on the right, and a series of steps. And they're all pretty focused on the production environment. Maybe it's a lake, maybe you do some data engineering, maybe you do some science, some visualization, some governance. And again, sometimes the fashion is to do it in Hadoop or Spark. Sometimes the fashion is to do it in Snowflake or Redshift or, Teradata. Over the years, fashions have changed, but they all have the same kind of architecture. And I think one of the things that we want people to think about is stop thinking so much just about what you do in production. Think about an architecture to change. Think about your right to repair this environment. And so the first part is to think about how you orchestrate and monitor / test all these tools in production so that you can tell if your data customers are getting something wrong before you get it. The second part is you think about how to deploy this, how to move from a dev environment to how many levels of environment you have into production. And then the third part is to think about how you manage your environments. And so this process, these 3 orchestrations, what happens in production, what happens in deployment, what happens in environments, are sort of 3 pipelines, 3 orchestrations that you need to do and to actually make really front and center in your data architecture discussion. And it's not us that agrees with this. You have to look at Gartner's recommends this very similar architecture of thinking about how to orchestrate, manage, and automate pipelines. And so the second part is that since the second bonus step is that if you look at how we do data and analytics, it's not just one group. Maybe in the middle here, you've got a lot of people doing data science and AI using tools, but there's other conferences focused just on data engineering. There's other conferences just focused on data visualization. There's data governance focus. But all of us in some ways are kind of working on different projects. We have our own subgraph, our own set of work that we're doing to get to the customer. Maybe you've got some people in IT practicing DevOps, working on a CRM and an ERP system and deploying it. Then you've got data engineers extracting it, loading it in a lake. Then you've got scientists applying an algorithm to that model and deploying it. Maybe you've got people doing Tableau to visualize, and then you've got the poor people in data governance trying to keep track of where all the data came from and what its meaning is. But your customer sees the end of all this. They don't know that there's this team structure and that they're organized. And the problem here is that there's a lot of collaboration complexity. And if you see this diagram on the very left, and the D means a development team. So you have a development team. Maybe it's got a BI person, a data science person, a data engineer, maybe in governance, and they're all working together. And I think here's where really Git can help. How do you have the data engineer and the data scientist, or multiple data engineers supporting a data scientist, not step on each other? So there's a collaboration that happens even in a team working for the same boss. But every organization has a development team, then they have a production team. They need to push that work to production. And it doesn't matter whether it's a model or some data transformation, you've got to have a way to deploy from your development team to production. And then there's a whole class of tools now that allow people to do the development work in a decentralized way. There's self-service BI tools, self-service data prep tools, self-service data science tools. And those tools themselves they work across the organization, and you can do almost everything that you want with a combination of sort of Alteryx and Data Robot and using Paxata or Trifacta or Tableau. And that's great because people are able to experiment quickly, and that's sort of one of the main ideas of iterative development. The challenge here is that these people also have to push to production. And so you end up with this kind of hybrid of you've got a centralized group pushing to production, you've got a decentralized group also pushing to production. So in Tableau, you can press a button and say to deploy on Tableau Online. So you end up with this almost mesh of different patterns of teams being organized. and teams deploying to production. And you have this sort of almost just a cornucopia of collaboration complexity in organizations. And most companies, unfortunately, are like the right. They have a lot of things going on. And again, the customer is at the end of this collaboration complexity. And so, you know, what I think is that you don't solve collaboration with a bunch of meetings. You don't say, okay, we've got to collaborate, so let's invent some Word documents and flowcharts and have more meetings. I think the software industry has really said that there's an architecture for collaboration. There's a way to make this work that actually minimizes the amount of meetings and maximizes the amount of empowerment that people can have to make changes themselves. And so just because this is the case doesn't mean you have to throw up your hands. It means that you can actually build a way to enable this collaboration within the artifacts that you create. And finally, the last step here of mine is to talk about getting analytic about what you do. And so all of us in data science and engineering and AI we're here to actually help use the power of data to help our customers make better decisions or make our customers you know, buy more, help more. And yet we're very unanalytic about measuring the work that our teams do. And so I think that's kind of ironic in that we should be focused on measuring the productivity of each of the team. How much have they done at productivity in an individual? How much errors are you having in production? How many errors does your data providers have? Are you meeting your SLAs? How fast are you deploying? How many release environments do you have? What test coverage do you have? And so, you know, you know, here's an example of a report that comes out of our software, being able to monitor these things on a per project basis. So for instance, you should look at, has my team been on time? What's the coverage of tests versus code? What's the error rates that I'm having in production? And there's a lot of ways for people to judge productivity, but, you know, from story points to deployment rates, but you should measure it. Because if you believe in analytics and your team gets big enough, you should be able to tell, be able to measure and monitor. And also, it's a great way for your team to agree. We have a lot of people with a lot of strong opinions in data science and analytics, but if everyone can sit and look at the data, it's actually much easier to get a bunch of cats on a team together to make a decision. And so what are some of the next steps with data ops? Well, first of all, think about what you're trying to do. The first is trying to, you know, accepting that you're going to live in a world where there's lots of errors, but not accepting that you have to, that's your lot in life, that you can change it, that there is a way for you to get ahead of these errors and operational challenges. And then second, think about how fast you can deploy from development to production. A lot of bigger organizations, it's a matter of weeks or months to deploy a model. How many models of yours have actually gotten into production? How many errors do you have? Do you know how many errors you have in production? And so I think by focusing on things that happen faster and better and happier, we can actually make the whole team and the whole system better. And so we've written quite a bit about data ops. We have again a manifesto with 18 points that we've had 7,000 or 8,000 people sign. We've written a cookbook that's free to download. That has we've got about 10,000 people get it. And then if you come from the software angle, you may know Gene Kim, who writes about DevOps and sort of the social environment around DevOps. And he wrote a new book that has a great story, a way of doing it that talks about this transformation in a data team. And so that's my, that's it. I think I'm running out of time. So if there's any, I appreciate you taking the time to listen to me, and thank you so much for attending. And if there's any questions, I'll look here on the side and see if there's anything I can answer. So I think we've got 2 minutes left. See, there's 40 attendees. That's fantastic. Anyone's got any questions? All right, well, appreciate everyone coming. Thank you for taking the time, and good luck, and hope you're enjoying the virtual conference. Oh, I do see it. So there's a question, and so I apologize. It says you mentioned that reusing code is important, but then you mentioned that copying and pasting is problematic. Can you expand on how you store, manage, and implement reusable code? Well, so for instance, let's take the case of you've got two Python files. I create one and then I send it to you, and so we've got two copies of Python files. So the first thing is that it's probably better that those Python files live in a source code repository together, and maybe they have different names and maybe they're alike. Or they're slightly different. And so maybe they're part of this process of the deployment pipeline and the innovation pipeline. So your customer's always demanding new features. And so it's important to work with your customers and say, look, we've got some what's called refactoring, and I want to take those two files and I want to make them into one file, make them into a function that works the same in both cases. And then both parts of the process will call that function with a set of parameters to say, and that way in software, there's a term called code bloat, where you take these very, very similar concepts and they end up being the same over and over and over again. And by refactoring, by refining, by actually reducing the amount of code, you end up taming that complexity. And so that's how you would do it. Take those two files, make a function, parameterize it, and then take those two files out of source control and then put in a new file and sort of cut in where those files are called into your process. All right, I finally found the question window. Is there any more questions I can answer? All right, well, I guess I'm done. So thank you much. Really appreciate it and have a great day.